Good day, everybody. Today I want to look at whether this vector field can be considered conservative. Most of the time it is not, although there is a scalar function whose gradient does give rise to this vector field. But the vector field, the domain it's defined on is not simply connected. So it's often said, well, then you can't be conservative because of that. But let me take a closer look. First, I'll look at a similar vector field to this, a couple of them. This vector field right here is, again, not simply connected in the plane. It's undefined at the origin. It kind of arises from what gravity would be like in a two-dimensional universe. If you think about in a three-dimensional universe, we basically have gravity an inverse square law, which is sort of like gravity gets weaker as the surface area of the mass distance increases, right? So if we think about the surface area of the sphere whose center is the sun and radius is from the sun to the earth, that's going to be 4 pi r squared. So it's kind of inversely proportional to the surface area. So if that gives the magnitude of the force and then its direction, if you put the mass at the origin, it's towards the origin. Then if you know the magnitude and direction, then you know the force. And we can, in this case, it is considered conservative. Well, it's actually even simply connected in R3. But we do have a potential. And back to R2, this is not simply connected in the plane, this vector field. Again, at the origin, there's trouble, but it would be like gravity in R2. Inversely to the circumference is how you'd expect the gravity to decrease in R2. So if you know the magnitude, the direction, you can get the force, and we can get a potential as well. So this one's not simply connected, but it is conservative. There's never any trouble. So if I look at the F1, F2, or I like to use P and Q components of the field, take their partial derivatives, they'll match. Well, I should say P sub y is the same as Q sub x, the mixed partials, in other words. So it satisfies that, but the domain is not simply connected. There's trouble at the origin. Plot of the vector field, and if I kind of fix the field strength, but for the arrows, and I'm going to do a little path here, say from 1/2 to 2.5. You can't really see it too well. There's 1, there's 2, there's 3. So I'm going from 1/2 to 2.5 in sort of a half circle. There's the description. So x is sine t, y is 3/2 minus cosine t as t goes 0 to pi. So at t equals 0, y will be at 1/2, and at t equals pi, y will be at 5/2. So it's that half circle. It takes me that path. And if you do the actual line integral, you get minus log 5, which is the same as evaluating the potential at where I finished minus evaluating the potential at where I started. Actually, so for the potential, I actually didn't use exactly either of these two. I actually used the negative of the natural log of the square root of x squared plus y squared. So I put the 1/2 in, but not the minus 1/2. Kept the minus out. But x was 0 at both endpoints. So it's essentially minus the log of the y value at where I finished, and then minus the log value of the y value at where I started. And of course, it's the same thing. pictorially. Here is the potential function. Here I did factor out the minus 1/2. And my path, well, actually I plotted the potential function two different ways. Just got the same thing. So there's the other way to think of the potential. And the path in the plane, went from x equals 0, y equals 1/2, and then along that half circle to x equals 0, y equals 5/2. But project onto the surface, you just have to evaluate f at where you finish minus f at where you start for the potential function. So that's what we did. So here's another path with the same endpoints, and notice we go around the origin, and the origin's not in our domain, so it's not simply connected. And here's the line integral. It came out the same, of course. And then here's the path. So we're going to start at the same x, y, z and finish at the same x, y, z. And the z, the f of x, y, is what really matters. F of x, y, where we finish, minus f of x, y, where we start. This is the graph of the potential function. So it's the same. So it doesn't matter how we got there. If I plot both paths, here's both paths. I'll put one in black so we can see. It is path independent, and the integral around every closed curve will be 0 as long as the path doesn't go through the origin itself. But it doesn't matter if it encloses the origin or not. So simply connected is a little bit overkill. It's kind of directed at one vector field, and that's this vector field. Again, the p sub y and q sub x are equal, which means we would normally say it's conservative. We can find a potential, and I say we can find a potential. It's the field plot. It decays rapidly, but if I plot it field strength going with logarithmically, you can kind of tell, well, if you just go around a closed curve, you're always going maybe with the field. There's no way you're going to get 0. So and then the theorem usually goes, well, because it wasn't simply connected, it's not a conservative vector field. But wait. Let's look at some curves. So, well, there's the circle. And that gave me 2 pi. I guess maybe I'll come back to that. I don't remember. But really, the potential function is actually the angle. Sometimes called the angle function. So, for example, the angle where I start here is, you'd probably say 0. It's a good place to put the 0, positive x-axis. And then if I go to the point 1, 1, well, that angle is pi over 4. So the change then in the function is pi over 4 minus 0, which will be pi over 4. And if you do the line integral for this path, we do get pi over 4. So let's look at the potential for this vector field. Sometimes arctangent of y over x is used as the potential. And arctan of y over x works, its domain is only quadrants 1 and 4. And then the angles in these two quadrants go from negative pi over 2 to positive pi over 2. So this function of x and y is defined for positive values of x. Another function we can do, right, so there's the range, it's defined for positive values of x. Another function we can do is the arccotangent of x over y, which can also be done in terms of arctangent through trig rules. Now the function will take on values from 0 to pi, and the domain of definition is y greater than 0. And if I take the gradient of those potentials, you remember the derivative of arc cotangent or just arctangent, I can find the x partial of arc cotangent of x over y, or that's the same as pi over 2 minus arctan of x over y. So if I do the x partial, I'll get negative y over x squared plus y squared. And if I do the y partial, I'll get positive x over x squared plus y squared. Or for the arctan of y over x, if I do the x partial and y partial, either way, I'm getting that vector field. So there is a function whose gradient gives me that vector field. But it's only defined on half planes. But we can do better. It's not too well known. You can define it on all points except for the positive x-axis and the origin. So any point in R2 that is not on the positive x-axis or the origin, and then the range of the function is 0 to 2 pi, but open. Right, so not including either of those two. But it's pretty good. And then here's the rule to get the angle. So that'll give you the angle of any point. And you can also put it in terms of arctangent. You could also, instead of this domain, everything except the positive x-axis and the origin, you could ignore everything but the negative x-axis and the origin, and use this arctangent function. The range now, instead of being 0 to 2 pi, is negative pi to pi for the value of this function. Its gradient will still give us the function. It's pretty tedious, but if this is the function, and if you do the x partial derivative, it works out. If you do the y partial derivative, it works out. So the gradient does give me that f. So now I'm almost on the full plane. Everything except a ray from the origin, essentially. And similarly for this function, the arctan one, if I do the x partial, I get what I'm supposed to get. And if I do the y partial, I get what I'm supposed to get. So both of those functions, they do give the angle of whatever angle you are from the positive x-axis, those functions will give them. But in quadrant 4 and quadrant 3, it could be up to pi over 2, or it could be for negative angles. A quick little plot of those functions. So here's the arctan of y over x. That's in quadrant 1 and 2. Quadrant 1 is these positive, or quadrant 1 and 4. There's the negative. Looks like it's going up, but if you go radially away, the z value doesn't change. It's actually a little easier to see in this form. So this is the same surface, and if you go radially away, the z value doesn't change. And you can cover the entire half plane that way. The arc cotangent, that's quadrant 1 and 2, and going from 0 to pi, instead of negative pi over 2 to pi over 2. At any point will just give me the angle to get to that point from the positive x-axis. And then the arc cotangent function, that goes 0 to 2 pi. I'll do this one first. And it's discontinuous. It doesn't show up too well. The function can't handle it. But so it goes from 0 to 2 pi. And then, well, then what's going to happen, right? You reach the same x value. You're supposed to jump down. So it tries to connect it. Essentially, it's the graph of a helicoid from 0 to 2 pi. Again, so, and it's discontinuous on the positive x-axis and the origin. So this surface represents the function. That could be its potential. I put it right here as well. And similarly with the arctangent graph, this graph goes negative pi to pi. And again, it should be discontinuous. Looks a little better. Graph is the helicoid. And it's continuous everywhere except on the negative x-axis. But you can use this surface as a potential. So let's try and use that surface as a potential. I'll use the cotangent one that goes from 0 to 2 pi. So there's the graph. I can show the discontinuity if I do the plot in two parts. So I do the negative y and the positive y separately and then put them together. So here we go. And here's like a equals 6. So that's the angle. So if the angle is 6 radians, that's going to stay on the surface. Or if I change it to, say, 2. Right, so if you pick any angle and just go radially out, you're going to stay on the surface forever. Now back to this curve. If I project it up to that surface, it's going to look like this. So I project that curve up to the surface, and then it's just where I finish minus where I start. It looks a little better if I do it instead on this helicoid, and I went past. That's a little preview of what I'm going to do. So this helicoid spiral ramp can go forever up and down. And so then if I plot the one function that only goes 0 to 2 pi and doesn't include the positive x-axis, there's what that looks like. So again, the spiral ramp with that one curve that goes from 0 to 1, 1. So project it up to the surface, and we just want the change in the value of the function. So let me look at another curve. So now I'm still going from 1/2, 0. I realize I just said 0, 1/2. It was 1/2, 0. Going from 1/2, 0 to 1, 1. So before, the change in angle was pi over 4. This has angle 0. This has angle pi over 4. But now if you go all the way around, you went 2 pi plus pi over 4. So that's 9 pi over 4. And so with that x and y, if you do the line integral, we do get 9 pi over 4. If I put it on the surface, you can see what's going on. So now I had to go beyond that argument function. So this isn't really legitimate to do with that function of x and y because it can't keep going past the positive x-axis. But if you think of this helicoid as the potential, it kind of does work, right? So if I just evaluate where I am, the z value on this surface as I curl around, it is just the change in the z values on the surface. That'll give me the change in angle. And what about closed loops? So here's a closed loop. I start here at 1/2, 0, and then I go on this inside part, keep going until I reach this end, and then I come back and finish right where I started. So that is a closed loop. It does not contain the origin, and the integral will be 0. Here's a plot on that helicoid surface, if you can follow it. So we start on the inside, we go up, and then we come back down where we finished. So unlike the previous one where we stopped up high, here we come back down and actually finish where we started on the surface. If I compute the line integral, I had Maple do it for me. Actually simplified quite nicely, so just to take a look at what x was. So x, to get this crazy curve, is x and y. And I wasn't going to do that myself. Just had Maple do the dx, dy, and then the integral of negative y dx plus x dy, or x squared plus y squared. Actually simplified amazingly, and did give me 0. Look at one more similar one. So here I start here and I go up and come back, but rather than go back where I started, I finish right here. It's still, if I look at the change in angle, this has angle 0, this has angle 0, and we curled around. We kind of didn't include the origin. If I project it to the surface, now I have to do a more general surface than just the what I called arg3. But so we go up, and then we come back down, and we are in a different spot, so it's the value of the function at where we finish minus the value of the function at where we started. But the angle is 0 at both points. And as long as they were the same angle, that's all that really matters. But they were both 0. Yeah, well, if you want Maple to do the work, it's still 0. If I go back to the 2 pi one, well, it's going to be more like the 9 pi over 4 one. It'll be like this one where I finished just above. So again, for this curve, x is cosine, y is sine. The angle is always t, and then as t goes 0 to 2 pi. And if I put it on the helicoid, bird's eye view, looks like I did the completed circle. If I can get it just right. But on the surface, you went around and you didn't come back. Right? That's not how I reached this endpoint. If I would have come back and reached the endpoint that way, then the integral would be 0. So I guess the helicoid can't be a function, doesn't pass the vertical line test, but you can still use this function or the other one. So either of these two functions, depending on what you want the range to be, although it doesn't matter because you're subtracting. So where you finish minus where you start, it doesn't matter which of the two you use, whether you go negative pi to pi or 0 to 2 pi. Where you finish minus where you start will be the same, although you're not allowed to cross that ray. Now this is an open domain, so you do have an open domain. So for any curve in this open domain, or any closed loop in this open domain, the integral will be 0, or it'll be path independent for any two curves that stay in the same domain. And I sort of like the 0 to 2 pi one myself. That's the arc cotangent one. And the plot is something like that. And again, it's continuous as long as you don't cross the negative x-axis or the origin. But for any other curve or closed loop in the plane that doesn't cross the positive x-axis, did I say negative? The positive x-axis for this one, then it will be path independent for those curves, or you will get 0 for any loop that doesn't cross the positive x-axis. And actually, I kind of showed more generally, as long as for closed loops, as long as the loop doesn't contain the origin, you'll actually be okay too. Because there's some way that we can kind of use this helicoid as a potential function. Just don't know how to do it in a textbook yet. So again, to me, the vector field is conservative on that open domain D, depending on what you want the open domain D to be. Could be here or here. And I think simply connected is a little bit overkill, and we don't use it for other vector fields like that radial vector field. There's no worry there. All right, so for the gravity one, a related one, all right, if you think it didn't go to 0 fast enough, here's another vector field. This could be the P, the Q. P sub y does equal Q sub x. It would be the gradient of this potential. Now notice again, the domain for the vector field is not simply connected. There's trouble at the origin, and it blows up even more at the origin. But it's actually still conservative as long as your path doesn't go through the origin. But here it doesn't even matter. You can go round and round and round, and it'll be where you finish minus where you start. Every closed loop will have integral 0, regardless of whether it included the origin or not. So simply connected is kind of just a way to take out that one exception. But that one exception, I think, is actually exceptional, and maybe we should think about it a little more and trying to work on getting a better potential. I know the problem with this potential is it's not a function, but it is a surface. All right, not long enough. So thanks for watching, and have a good rest of your day.